Chapter 6 Thermodynamics to be continued as Part D. In this last part, we will study the thermal cycles, the heat engines and refrigerators, and the second law of thermodynamics. After we studied the thermal processes, we define the thermal cycle as a group of thermal processes which the gas undergoes and returns back to the same initial point. To have this thermal cycle and this study, we have two conditions. The first condition, to have an ideal gas, so as I can use all the equations of the ideal gas and the state equation of the gas. The second condition is that each process to be reversible. What is the meaning of reversible? Let's check what is the meaning of a reversible process. For a thermal process to be reversible, imagine we have a thermal process from 1 to 2. If I reverse the conditions of the process and I return back from 2 to 1 exactly, this is called a reversible process. So from 1 to 2, this is the relation between P and V. The gas changes its state from state 1 to state 2, and it gains amount of heat energy Q. If I reverse the condition, which means that the gas loses Q, the same amount of heat, it returns back from 2 to 1 exactly. This is called a reversible thermal process. But if the gas returns to a point near point 1, not exactly point 1, 1 dash, this is called irreversible process. So the reversible process is defined as the process in which the system returns back to its original conditions if the process is reversed. So the two conditions to study a thermal cycle is to have an ideal gas and a reversible process. For a thermal cycle, we said that we will start from point A and make some changes or some thermal processes till we reach point C. These thermal processes are expansion because we increase the volume V. So this part from this path from A, B, C is called expansion because the volume is increasing. If the volume is increasing, the gas needs to absorb amount of heat. This amount of heat, we will denote it by QH. So QH is the amount of heat energy absorbed by the gas during expansion. Now, the second part of the cycle is the contraction part. I have to contract or compress the gas so as to return back to the same point. To contract the gas through the path CDA, this path is called contraction because the change in volume is decreasing. Volume is decreasing. To decrease the volume, we remove amount of heat from the gas. So there is amount of heat lost or rejected or repelled by the gas. This amount of heat will be denoted by QL. Note that QL is with negative sign, but now when dealing with QL, I mean the amount of or the magnitude of. So I will always take the QL is the absolute value of the amount of heat repelled or rejected. From the PV graph, QH is greater than QL. Why? From A to C, the same amount of change in internal energy. And the work A, B, C is the area under the curve. But the work CDA is the area under the other curve CDA. The work ABC is greater than the work CDA. So QH is greater than QL if I apply the first law of thermodynamics. Note that for any cycle, the change of internal energy is zero. We explained before that the change in internal energy is a state function. It depends on the initial state and the final state only. So I will begin the cycle from point A and I will return back to point A. So the initial state is A and the final state is A. So delta U will be zero. Also, the change in entropy is state function. It will be zero if my cycle is having the two conditions of the ideal gas and the reversible process. I want now to calculate the Q for the whole cycle. The Q for the whole cycle will be by adding QH and QL. But now I am denoting the QL with absolute value or the amount of heat energy rejected. So the Q of the cycle will be the amount of heat energy gained minus the amount of heat energy lost. This will give you the Q of the cycle. And from applying the first law of thermodynamics, Q of the cycle equals delta U of the cycle minus W of the cycle. So if delta U is zero, you will find that Q of the cycle equals work of the cycle. To summarize this up, we can say that for any cycle, we don't have change in internal energy, so the heat equals the total work. Total heat equals the total work. And the total heat equals QH minus Q. How can I draw the cycle in the PV and the TS diagram? When I'm drawing the PV diagram, I will draw a part of expansion till reaching the maximum volume, then part of contraction till reaching the minimum volume. And the area enclosed in this cycle will resemble the area of this area is the work done by the cycle, the work done by the gas through the cycle. So the work net or the work cycle is the area enclosed by the closed cycle in the PV diagram. Now I will draw the same cycle but in the TS diagram. In the path A, B, C, the gas absorbed amount of heat called QH and it increases its volume and its temperature. So when drawing A dash, B dash, C dash, I will draw a path of increasing T. Temperature at A is less than the temperature at C. That's why I draw the path like this, because there is increase in temperature. And the gas is absorbing QH. When decreasing the volume, also the temperature is decreasing in the path C dash, D dash, A dash, and the gas is rejecting QL. Remember that the area under the TS diagrams refers to the heat energy. So the area enclosed by the cycle in the TS diagram is the Q of the cycle or the Q net. But we said before that for a cycle, Q cycle equals work cycle. So we can say that this area in the PV diagram is the same area in the TS diagram. Of course, you have to put your units of the T and S and your exact units of the P and V. So the work cycle equals the Q cycle equals QH minus QL equals the area enclosed in the PV equals the area enclosed in the TS diagram. Note that sometimes we say Q net and work net instead of work cycle and Q cycle, which means that it's the net work and the net heat energy. Now we will explain the heat engine. What is the heat engine? The heat engine is the application of the thermal cycle. This is the engine that changes heat energy to work. The aim of the heat energy is to change the amount of heat to the work that I can use in my motor or compressor or whatever. So you will have to get a cylinder containing a perfect gas and a piston, as we mentioned this before. Now the piston at this volume is at point A. I will give the gas QH, amount of heat energy. So it will expand, making work till reaching the point C. This is the half of the cycle. A, B, C. The piston reaches the point C after thermal processes A, B, C and gaining QH. Now I converted the heat energy into work, but for the motor or the engine to refunction again, I have to return back to the same point A to make a cycle, to repeat the cycle. Returning back from point C, point A using mechanical hand means compression or decreasing of the volume, and the gas is rejecting QL. This is the second part of the cycle CDA. So the heat engine is the application of the thermal cycle. I have half the cycle expansion and the other half contraction. Take care that the cycle is always clockwise. In order to sketch the heat engine, we will sketch it as follows. We will have TH and TL and a circle between them. TH means the hot temperature reservoir and the TL is the cold temperature reservoir. We have a heat engine working between TH and TL. It is absorbing QH from the hot reservoir and repelling QL to the cold reservoir and giving us the net work or the work of the cycle. This is a simplified diagram for the heat engine representing how it is absorbing QH from the hot reservoir and rejecting QL to the cold reservoir, giving me my required work or mechanical work. For any engine, it is explained by its efficiency. What is the efficiency of this engine? The efficiency is the ratio between the output and the input. So we define the efficiency of these engines as the work net divided by the QH. This is the output. This is the outcome. This is what I want from the engine. I want work. And I am giving the engine QH, which is burning a fuel and giving and giving heat to the gas. So by definition, the efficiency of the heat engine is the work net divided by QH. But remember that the work is QH minus QL. I know that It is absolute value, but we said before that if I don't write the QL, I mean that it's amount of heat rejected. Dividing QH minus QL over QH will be 1 minus QL over QH. This is the other form of the efficiency of the engine. We have another representation of the engine using the output power. It is very common to talk about the engine with the output power. What is the power? The power is the rate of change of energy. So if you, in the problems, the problem is talking about power, we define the power as the rate of change of energy. So we will draw the same diagram, TH, TL, and a circle representing the heat energy and the output power instead of the output mechanical work. If you draw the diagram like this, draw QH dot and QL dot. What is the meaning of the dot? Meaning rate of heat energy gain and rate of heat energy lost. So if you want to represent the heat energy using the power is the work net dot. Dot means divided by time. And also use the same equation but use all the energy you have divided by time. So the work equals QH minus QL. Now work dot equals QH dot minus QL dot. And the efficiency will be work dot over QH dot, which is the power over QH dot. Again, the symbol dot means rate of, means I'm dividing the energy with time. Okay, this was the heat engine. The heat engine is the application of the thermal cycle. It is using the heat or transferring or changing the heat into mechanical work or mechanical. I can use the reverse cycle to have the refrigerator application. Reverse cycle or refrigerator. The reverse cycle is directed anti-clockwise, counterclockwise. So I will go to point C through point B, but with less work, and then return back from CD to A with greater work or greater amount of work. While going from A, B, C, the gas has to absorb amount of heat. Now the gas is absorbing QL and rejecting QH. To symbolize this, we symbolize the refrigerator as a circle working between two temperatures, TL and TH. Now the refrigerator needs work to run. So you have a compressor running the refrigerator. So you are giving work. Take care, this is the arrow. You are giving work to the refrigerator. This is negative work. What does the refrigerator do? It is absorbing heat from the low temperature reservoir and rejecting heat to the high temperature reservoir. So the expansion is now heat absorbed is QL and heat rejected is QH. Of course, we mean amount of heat. Now the work of the cycle is negative, and we want to explain the performance of the refrigerator using the coefficient of performance. For the refrigerators, we don't calculate the efficiency, we calculate COP, which is the coefficient of performance of the refrigerator. Again, the coefficient of performance is the output divided by the input. I am running a compressor, I'm giving work to the refrigerator, so this is the input. And what is useful for me is the amount of QL absorbed or absorbed by the refrigerator. So the COP of the refrigerator is QL over the work. Again, QL over the work. So QL over QH minus QL divide by QL in the upper and lower. So it is 1 over QH over QL minus 1. This is the refrigerator. Sometimes it's not used, the reverse cycle is not used as a refrigerator. It is used as a heat pump. What is a heat pump? A heat pump is using this amount of expelled heat to use the heat for warming up. So it is called a heat pump. When dealing with the heat pump, what is useful for me is the QH. So the reverse cycle, if you are using it as a heat pump, its COP will be QH over W. But if you are using it as a refrigerator for cooling, so you are using QL over W. Now, after explaining the cycle and the reversed cycle, we have combination of both. For example, if we have a car provided with an air condition. If you have a car provided by an air condition, you have an engine. This is the car engine. The car is taking QH from the TH and repelling QL to the atmosphere and giving us net work. This work is the mechanical work which the car is using to move. But also we can take a part of this work and use it as a refrigerator. Refrigerator here means the air condition of the car. The air condition of the car is working between 2 points, the TL and the TL dash. TL dash is the temperature of the car inside, the inside of the car. But the TL is the atmosphere temperature. This is a car provided with an air condition. One of the famous cycles used in thermodynamics is a theoretical reversible cycle is the Carnot cycle. The Carnot cycle consists of 4 thermal processes, 2 isothermal processes as shown in the PV diagram, and 2 adiabatic processes as shown in the PV diagram. So I have a gas, an ideal gas, in my cylinder, and I have a piston. First, we have isothermal expansion from point A to point B, then adiabatic expansion from B to C. This is the part of expansion. This is A and this is C. In this part, the gas is absorbing amount of heat QH. In the second part of the cycle, I have from C to D isothermal compression, and then from D to A, I have adiabatic compression. So the second half, which is the compression of the gas is rejecting QL as we explained before in any cycle. And of course, the area enclosed by the cycle is equivalent to the amount of the work of the cycle. Now we want to draw the same cycle in the TS diagram. In the TS diagram, I have A to B isothermal process. From A to B isothermal process, is a horizontal line at constant temperature Ts. Then from B to C, it's an adiabatic process. It will be a vertical line because in the adiabatic process, we don't have change in entropy. So drawing ABC in the TS diagram will be A, B, C, a horizontal line, then a vertical line. Then the second part of the cycle, while contracting, I will draw the isothermal again as a horizontal line, but at a lower temperature TL. From C to D, I will draw this line. And then adiabatic, again, I will have it a vertical line. So drawing the PV in the TS for a Carnot cycle will be a simple rectangle as you notice. The area enclosed in this rectangle is equivalent to the amount of net heat energy. From A to B, the gas is absorbing QH. From B to C, it's adiabatic, so no heat energy is absorbed. So QH is the area under AB. If I want to calculate this area, I'm calculating the area of all this rectangle, this big rectangle. This area is TH multiply delta S. While from C to D, I will calculate this area only. This area is TL multiply delta S. So if you want to calculate QH, it is TH multiplied delta S. And QL is TL multiply delta S. Divide both equations, you will have QH over QL equal TH over TL. This is only for a Carnot cycle. This property, which is QH over QL equals TH over TL, is only for Carnot cycle. Now, when calculating the efficiency of Carnot cycle, I will calculate the efficiency of any engine. So the efficiency of any engine will be work divided by QH, which is 1 minus QL over QH. But for Carnot, QL over QH could be substituted with TL over 2TH. So for Carnot, I can use the temperatures instead of the heat energy. I have some remarks about the Carnot cycle. The first remark that the efficiency of Carnot is the maximum efficiency possible between two temperature TH and T. Also, the efficiency of Carnot depends only on TL and TH and not on the kind of gas. Number three, you don't have any efficiency of 100%. It is impossible to have an efficiency of 100%. Why? To have an efficiency of 100%, you have to put TL equals 0 Kelvin, and it is impossible. Or to put TH equals infinity, and this is also impossible. And this says that the reversible efficiency is greater than the irreversible efficiency. Carnot cycle can be used also as a reverse Carnot cycle. We can use it reversed and use it as a refrigerator or a heat pump and calculate the COP of the Carnot. Again, when calculating the COP of Carnot, we can calculate it using the temperatures instead of the heat energy. Now we want to discuss the second law of thermodynamics. The second law of thermodynamics has three statements. It's a kind of statement, it doesn't have an equation. The first statement is called the Kelvin-Planck statement or the heat engine statement. This statement states that it's impossible to have an engine that absorbs QH and gives you work without rejecting QL. If you draw this without QL, you mean QL is zero, this is impossible. Why this is impossible? Because QL is needed to be rejected to return the piston to its original point A. This is the Kelvin-Planck statement. Another statement for the second law of thermodynamics is called the Clausius statement. Clausius statement is describing that if you want to make a refrigerator that is operating between TL and TH, and you will use the refrigerator to absorb QL and reject QH without work, this is impossible. Could not be done. And this is, of course, because you cannot just transfer heat from a cooler body to a hotter body. This is impossible. The last statement of the second law of thermodynamics is the modern statement or the entropy statement. This states that the entropy of the universe is always increasing. Remember that when we were talking about the thermal cycle, we said that the change in entropy equals zero. This is only done for irreversible processes. But if we have irreversible processes, the change of entropy must increase than the zero. So the entropy is increasing, but never decreasing. Now we want to prove that Carnot cycle is a reversible cycle. Reversible means that the change of entropy equals zero. So we will assume that Carnot cycle is operating between TH and TL. The engine is absorbing QH, giving work and rejecting QL. From Carnot, we know that QH over QL equals TH over TL. I will get the change in entropy of the hot reservoir and then get the change of entropy of the cold reservoir, then add both to get the total change of entropy of the system. The first step is calculating the change of entropy of the hot reservoir, delta SH. Delta SH equals Q over T. But now the hot reservoir is losing energy, so I will put negative because the hot reservoir is losing an amount of energy QH. As for the cold reservoir, it is gaining QL, so the change in entropy of the cold reservoir is positive. Positive QL over TL. Add both equations to calculate the total change in entropy of the system. Delta S total equals delta SH plus delta SL. When adding both, you will find it equal to 0. Why equals to 0? Because QH over QL equals TH over TL. So QH over TH equals QL over TL. Now I am adding QH and QL over TL, but this is negative and this is positive. So the addition is 0. Now we want to prove that heat transfer is irreversible process and the change in entropy is greater than 0. When you have two bodies, one of high temperature and one of low temperature, we explained before that the hot body will lose amount of heat and the cold body will gain amount of heat. So the hot body will lose QH and the cold body will gain QL. Calculate the change of entropy of the hot body and the change of entropy of the cold body then add them together to get the total change of entropy of the system. The change of entropy for the hot body is losing, so I will put negative QH over TH. As for the cold body, it's gaining energy, so the change in entropy will be positive QL over T. Add both to have the total change in entropy. When adding this and this one, we know that the amount of QH equals the amount of QL, but TH is greater than TL. So this value will be greater than 0. Delta S total is greater than 0. This was the last part of chapter 6 of the thermodynamics. Next two videos will be examples on chapter 6 in the thermodynamics. We will have enough examples on the thermal processes, the thermal cycles, and the second law of thermodynamics. Thank you for listening.